Hey everyone, my name's Sam Moore, and I'm with the General Robotics Lab at Duke University. And I'm going to be telling you about some work I've been doing with learned MPC for legged robots. And kind of due to the time constraints, there's kind of two main things I want you to take away from this talk. And the first one is that I'm going to tell you about two kind of more practical inductive biases that we've come up with that can help you, that help enable learned MPC for legged robots. And the second one is really how we integrated these inductive biases within a larger model-based RL framework that can help us combine some of the benefits of deep learning and model predictive control. So what these inductive biases do, I told you they're more practical, and they both aim to address non-smoothness in learned MPC. And we noticed non-smoothness was a key difficulty in two parts of the learning process. The first is in the learned model itself. So if you're trying to learn a model for a non-smooth system, that non-smoothness will be replicated in the neural network or whatever you're using to replicate those dynamics. Secondly, because you're collecting data from a non-smooth system as a whole, there's going to be non-smoothness within the training data itself. And so to address non-smoothness in the learned model, there's really two components that, two kind of sub areas that are the causes of this non-smoothness. And we address them with what we're calling the smooth neural surrogate dynamics module. And what this model does is uses Lipschitz-based weight regularization to constrain the global smoothness of the network. And there's, like I said, two scenarios where non-smoothness is a key consideration. One is like a physical scenario. We're trying to model non-smooth dynamics. And so we want to smooth that out to enable better online optimization. The second scenario is that neural networks are notorious for having this kind of artificial local irregularity just from the learning process itself. And what smooth neural surrogates do is they smooth out both of those globally so that online optimization is much easier. Secondly, non-smoothness in the training data we address by revisiting our assumptions with the loss function. Typically, if you're trying to learn dynamics, any sort of supervised learning, you'll probably gravitate towards Gaussian negative log likelihood or mean squared error. But what we noticed is that the error residuals for, especially in the legged robot cases we looked at, they were much more closely Cauchy distribution as opposed to a Gaussian. And the difference there is that a Gaussian distribution it is defined by the mean, and the Cauchy defined by the median. Gaussian has the variance, and the Cauchy has a median absolute deviation. And actually, the Cauchy variance is completely undefined. And what that enables it to do is capture these more discrete jumps in the data itself and enables much better learning, much more stable convergence overall. And so I'll go into, if you want to talk about more quantitative things, check out the paper later, but just visually, these are kind of some of the scenarios you'll see where like the smooth neural surrogate can easily model things like, just basic sideways trotting where the standard neural network might fail. And kind of a side-by-side on the heavy-tailed loss function is that, I guess I should say that the smooth neural surrogates really help mitigate these catastrophic failures where your network is basically deceiving your optimizer in what should happen. And what the heavy-tailed loss functions do is really kind of enable precision. Let me play this again. They really enable precision. Sorry, there we go. And this is just bounding ahead at like 0.5 meters per second. And you can see the heavy tail loss function trained one is much more precise. And so how we integrate these kind of two straightforward inductive biases within a broader system is a pretty standard model-based RL framework where we can replace the policy with a model predictive controller and a state estimator that are both learned from scratch. And we use an actuator network to capture some of the sim-to-real differences. But we do something that's different than classical MPC in that we add in domain randomization to help our model learn across the various scenarios that it might encounter in the real world. And kind of what that looks like is we only train these models on randomized incline even terrain. So the terrain they're trained on is completely flat, but different inclines. But it generalizes pretty well to rough terrain, certain steps, and more interestingly, I think, is that you can use different cost functions than you use during training. Now, this might be like pretty intuitive, like something you should be able to do with model predictive control. You just swap the cost functions, everything works. But if you're only collecting data, for example, of your robot doing trotting, and that's the training data you use to learn the dynamics, then you're not going to be able to guarantee that those dynamics then can be used to do galloping when you switch the cost functions. And so with these smooth neural surrogates, we were able to do a bunch of different behaviors with different cost functions in different environments. And of course, we validated these on the real world, most of these behaviors, and we saw pretty, pretty good performance overall with, again, trotting over varied terrain. And this is all like blind locomotion, by the way, just completely blind locomotion over varied terrain, different payloads, going down like a step or two, and like mid-stride costing constraints you generally should be able to do with learned MPC, but can remain challenging, as I mentioned earlier. All right, so if you're interested in learning more, I have a full paper available with more demos and everything that you can check out with the QR code there. And then lastly, before I'm done, I just want to plug my my lab mates paper that was just accepted in Science Robotics. And we're a new lab, so I have to shamelessly plug some new work. And this, because this is like the coolest robot I've seen in real life. And I encourage you to go check out their work as well.